decisions, and uncertainty. The statistical and computational methodology that we develop for assessing models about jury selection fit into general framework of decision-making that we call hypothesis testing. Using a statistical test as a way of making decisions is a standard in many fields and has a standard terminology. In this section, we're going to describe the general sequence and steps used in statistical tests along with some terminology. Our example is from biological science, and you're going to see that the statistical and computational steps in the process are consistent with the corresponding steps in our analysis of data from the legal system. However, the biological data are about plants, not human beings, and justice. So the context and interpretation of the calculations below are very simple. We're going to talk about the Mendel model. Mendel is recognized as a founder of the modern field of genetics. Mendel performed careful and large-scale experiments on plants to come up with fundamental laws of genetics. Many of his experiments were on varieties of pea plants. He formulated sets of assumptions about each variety. These were his model. So those data are basically create a model. He then tested the validity of his models by growing the plants and gathering more data. For pea plants of a particular variety, Mendel proposed the following model. For every plant, there is a 75% chance that it will have purple flowers and a 25% chance that the flowers will be white, regardless of the colors in all the other plants. So this is his propositions or hypothesis. To see whether his model was valid, Mendel grew 929 pea plants of his variety. Among these 929 plants, 705 had purple flowers. So these are the information that we are having. Eventually, we're going to create some hypothesis testing and check to see if it satisfies the hypothesis or not. We're going to use this data to perform a test of hypothesis and see if Mendel's model looked good or not. In the very first step, the hypotheses are going to be defined. So as we talked before, we have null hypothesis and alternative hypothesis. All statistical tests attempt to choose between two views of the world, especially the choice between two views about how the data were gathered and generated. These two views are called hypotheses. The null hypothesis is a clearly defined model about chances. It says that the data were gathered or generated at random under clearly specified assumptions about the randomness. The word null supports the idea that if the data look different from what the null hypothesis predicts, the difference is due to nothing but chance. From a practical perspective, the null hypothesis is a hypothesis under which you can simulate data. In the example about Mendel's model, for the color of pea plants, the null hypothesis is that the assumptions of his model are good. Each plant has a 75% chance of having purple flowers, independent of all other plants. Under this hypothesis, we can simulate random samples by using sample underscore proportions. The alternative hypothesis, this says that some reason other than chance made the data differ from the predictions of the model in the null hypothesis. In the example about Mendel's plant, the alternative hypothesis is simply that his model isn't good. So let us move on to step 2. In step 2, we have the test of statistics. In order to decide between the two hypotheses, we must choose a statistic that we can use to make our decision. This is called the test statistic. We briefly talked about test statistic in previous lecture. We will be comparing two categorical distributions, the one in Mendel's model and the one we will get in our random sample. We want to see if these two distributions are close to each other or far apart. So a natural test statistic is the total variation distance, or TVD, developed in the previous section. It turns out with just two categories, the TVD, or total variation distance, is rather simple and easy to interpret. For example, let's take a look at Mendel's model that says that the purple-white distribution is 75% and 25%. Suppose the distribution in our sample came out to be 70% and 30%. So let us do a little bit of algebra. Because there are only two categories, something interesting happens when they calculate TVD. First, notice that the absolute value of the difference between 70% and 75% is 5%. And the absolute value of the difference between 30% and 25% is also 5%. So the TVD, or the total variation distance, is basically a half of the distance between 70% and 75%, the proposed and the actual value that you got. And don't forget to use the absolute value. Plus, for the second category, you're going to do the same thing. It basically is 5%. That's just the distance between the two proportions of purple flowering plants. It's also just the distance between the two proportions of white flowering plants. So as you can see, the calculation of total variation distance with two categories is very simple. Now, if you do a little bit of math, this is true whether there are just two categories. The TVD is equal to the distance between the two proportions in one category. So a perfectly fine test statistic would be the distance between the sample proportion of purple plants and 75%, which is the corresponding proportion in Mendel's model. Since percents are easier to interpret than proportions, we'll look and work with percents instead. Our test statistic will be the distance between the sample percent of purple plants and 75%, which is the corresponding percent in Mendel's model. So basically, we're taking the absolute value of the sample percent of purple flowering plants and 75. Don't forget to take the absolute value to get a positive number. Otherwise, as we saw before, if you add all of those differences together, you get a 0. This statistic is a distance between the two distributions. It makes sense and is easy to use. A sample percent of around 75% will be consistent with the model, but percents much bigger or much less than 75 will make you think that the model isn't good enough. Therefore, small values of distance will make you lean toward the null hypothesis. Big values of the statistic will make you lean toward the alternative hypothesis. To choose a test statistic in other situations, look at the alternative hypothesis. What values of the statistic will make you think that the alternative hypothesis is better choice than the null? If the answer is big values, you have a good choice of statistic. So also if the answer is small values, but if the answer is both big values and small values, we recommend that you look again at your statistic. See if using a distance instead of difference can change the answer to just big values or not. Now let's talk about the observed value of the test statistic. The observed value of a test statistic is the value of the statistic you get from the data in the study, not a simulated value. Among Mendel's 929 plants, we saw that 705 had purple flowers. So the observed value of the test statistic was the absolute value of 100 multiplied by 705 divided by 929 minus 75. This is basically give you the observed statistic, which is about 89%. So Mendel expected 75% of the plants to have purple flowers, and among 929 plants he studied, 705 had purple flowers. So if you do the division between these two, you get 75%. But the observed statistic is 89%. It tells us how much the actual proportion of purple flowers deviates from the expected proportion of 75%. In this case, the deviation is quite small, meaning that the Mendel's results are very close to the expectation. The observed proportion of purple flower plants, again, if you do the algebra, p hat is 705 divided by 929. And if you convert the observed proportion into a percentage, you basically multiply that by 100 and you get 75.88. Let's take a look at step 3, the distribution of the test statistic under the null hypothesis. The main computational aspect of a test of hypothesis is figuring out what the model in the null hypothesis predicts. Specifically, we have to figure out what the values of the test statistic might be if the null hypothesis were true. Now, the test statistic is simulated based on the assumptions of the model in the null hypothesis. The model involves chance, so the statistic comes out differently when you simulate it multiple times. By simulating the statistic repeatedly, we can get a good sense of its possible values and which ones are more likely than others. In other words, we get a good approximation to the probability distribution of the statistic as predicted by the model in the null hypothesis. So as with all distributions, it is very useful to visualize this distribution by a histogram, as we have done in previous examples. Let's go through the entire process here. So let us start by assigning some known quantities to names. Let us install the data science package, pip install data science. From data science, I want you to import table and make array. As you remember, table allows you to create and manipulate tables, and make array function helps you to create arrays of data. Now, let us make an array and set it to be Mendel underscore proportions. Now, what are we going to do? We're going to basically extract the first item, which is located at index 0, to the variable, which we call Mendel underscore proportion underscore purple. And remember that Mendel had 929 plants. This is going to be your sample size. We are simulating a distribution of a test statistic under the null hypothesis at Mendel's predicted proportions of plants with purple flowers to be 75%. It generates 10,000 simulated values of a distance between the observed proportion of purple flowers in the sample and the expected proportion, which is 75%, then visualize the distribution of those distances. So this is the line of code that you need to use to create a function to simulate sample proportions, and then define another function. Basically, it returns the percent of the distances between the sample proportion of purple and the Mendel proportion of purple, and simulate that 10,000 times. Then create a table with the distances and plot the histogram. So if we graph this and visualize this, this is the histogram that we see. Prediction made by null hypothesis. Now, please pay attention. The distances between the sample is 0% and 75%. Okay. The conclusion of the test. The choice between the null and alternative hypotheses depend on the comparison between what you computed in step 2 and 3, the observed value of the test statistic and its distribution as predicted by null hypothesis. If the two are not consistent with each other, then the data don't support the null hypothesis. In other words, the alternative hypothesis is better supported by the data. We say that the test rejects the null hypothesis. If the two are consistent with each other, then the observed test statistic is in line with what the null hypothesis predicts. In other words, the null hypothesis is better supported by the data. We say that the data are consistent with the null hypothesis. In our example, the observed value of the test statistic is about 89% and computed in step 2. Just by eye, locate roughly where 89% is located on the horizontal axis of your histogram. You'll see that it's clearly in the heart of the distribution predicted by Mendel's model. You can redraw the histogram with the observed value, and this is what we see here. About 89%, which is just close here. The observed statistic is like a typical distance predicted by a null hypothesis. The null hypothesis in Mendel's model. So our test concludes that the data are consistent with Mendel's model. Based on our data, Mendel's model looks good. What's the meaning of being consistent here? Do we have any algebra or statistical numerical value to associate with it? In all of our examples of assessing models, there has been no doubt about whether the data were consistent with the model's prediction. They were either very far from what the model predicted, as in examples about jury panels, or similar to what the model predicted, as in the example about Mendel's model. But outcomes are not always so clear-cut. How far is far? How do you answer this question? Now we need to talk about the p-value. Exactly what should similar mean? While these questions don't have universal answers, there are some guidelines and conventions that you can follow. First, it's important to understand that whether the observed test statistic is consistent with its predicted distribution under the null hypothesis, which is a matter of subjective opinion and judgment. We recommend that you provide your judgment along with the value of the test statistic and a graph of its predicted distribution on the null. That will help your reader to make their own judgment about whether the two are consistent or not. In our example, the judgment is clear, but suppose someone grew another 929 plants of some related variety and wanted to see if Mendel's model worked for plants of that variety too. What would you conclude if their observed distance came out to be 3.2? just right here. You see the red dot? Is the observation based on the new variety of plants consistent with the prediction in the histogram or not? Now, the answer is not so clear. It depends on whether you think the red dot is too far from the bulk of the predicted values to be consistent with the prediction based on Mendel's model. Conventional cutoff and p-value. If you don't want to use your own judgment, there are conventions that you can follow. These conventions tell us how far out into the tails is conventionally considered too far. The conventions are based on the area in the tail, starting at the observed statistic, the red dot that you saw, and looking in the direction that makes us lean toward the alternative. In our example, that is located on the right side, and you check that red dot as well. Because big distances favor the alternative, which says that the model isn't good enough. If the area of the tail is small, then the observed statistic is far away from the values most commonly predicted by the null hypothesis. Remember that in a histogram, area represents percent. To find the area in the tail, we have to find the percent of distance that were greater than or equal to 3.2, where the red dot is. The array distances contain the average for all 10,000 repetitions of random sampling under Mendel's model. And different underscore observed underscore statistic is 3.2. Now, if you run this line of code, you get about 3%. About 2.4 or 2.5% of distances simulated under Mendel's model were 3.2 or greater. Just 2.4%, just 2.5%. By the law of average, we can conclude that if Mendel's model were correct for these new plants, then there is about a 2.4, 2.5% chance of the test statistic would be 3.2 or more. That doesn't seem like a big chance. If Mendel's model is true for those plants, something quite unlikely has happened. This idea gives rise to the conventions. P-value. The p-value represents the probability of observing a test statistic as extreme or more extreme than one observed from your data, assuming that the null hypothesis is true. Small p-values, if you have a small p-value, less than 5% usually, it suggests that the observed statistic is likely to have happened by chance. If the null hypothesis were true, you'll likely reject the null hypothesis. Then you have large p-values. If the p-values are large, then the observed statistic is consistent with the null hypothesis and you would not reject the null hypothesis.